Have you ever wondered how mathematical modeling impacts our daily lives? Well, it's a powerful tool that intertwines mathematical theory with real-world data to predict behaviors and analyze systems with precision. It's like a secret decoder ring, unlocking the patterns and dynamics hidden within the complexities of life around us. From the rise and fall of animal populations to the spread of infectious diseases, from the ebb and flow of economies to the far-reaching effects of climate change, mathematical modeling helps us understand, predict, and navigate these phenomena. It's even used to optimize traffic flow in bustling cities and to analyze the diffusion of information across social networks. Simply put, this tool allows us to represent the world in equations and simulations, providing a clearer vision of the intricate systems that shape our lives. So, if you're ready to explore the art and science of mathematical modeling, buckle up. Now let's dive into 10 fascinating topics related to mathematical modeling. First, we explore population growth modeling. At the heart of this concept lies differential equations, mathematical tools that allow us to describe the change in populations over time. Imagine a group of rabbits in a field. Given their high reproduction rate, the population can grow rapidly, but only if there's enough food and space. To model this, we'd use a differential equation that takes into account the current rabbit population and the rate of change. These models aren't just for rabbits though. They're used across a wide range of scenarios, from human societies to microorganisms in a petri dish. By understanding the factors that affect population growth, we can predict future population sizes. This is vital for planning. Think urban development, resource allocation, even wildlife conservation efforts. So, population growth modeling isn't just about numbers. It's about understanding the dynamics of life itself, and using that understanding to plan and prepare for the future. This model is crucial in understanding population dynamics and planning for future needs. Next, we delve into disease spread modeling. This field of mathematics is fascinating, and it's also vital for public health. It's all about developing mathematical models that predict the spread of infectious diseases. These diseases could range from a common cold to global pandemics like COVID-19. Mathematicians start with data about the disease, how infectious it is, how long it takes to recover, and how it's transmitted. They use this data to create a model, often using differential equations. The model can then predict how the disease will spread through a population over time. These models are not just theoretical exercises. They are vital tools that help public health officials plan for and respond to outbreaks. They can predict when an outbreak is likely to peak, how many people might be affected, and how effective different control strategies might be. With these models, we can better prepare for and manage disease outbreaks. Our third topic is economic modeling. Imagine a set of mathematical tools which, when applied to economic data, can help us understand and predict trends in the economy. This is what we call economic modeling. It's like a compass guiding us through the complex world of economics. These models can be used to analyze a wide array of economic phenomena. For instance, they can predict GDP growth, inflation rates, or the impacts of different economic policies. They do this by using mathematical equations to represent the real-world interactions of economic variables. Think about how policymakers decide on interest rates or tax policies. They rely on these models to anticipate the potential consequences of their decisions. These models can also forecast the effects of unexpected events like a pandemic or a natural disaster on the economy. In essence, economic modeling is like a crystal ball, providing a glimpse into the future of our economy. Economic modeling helps policymakers make informed decisions. Now, let's consider climate change modeling. This fascinating application of mathematics uses complex equations and advanced computer simulations to study the effects of climate change. It allows scientists to understand and predict the impacts of rising temperatures, sea level rise, and the increase in frequency and severity of extreme weather events. These models are built on the laws of physics and chemistry, and they're refined with observational data from various sources, including satellites, weather stations, and ocean buoys. The models are designed to replicate past climate patterns and predict future ones. The goal is to anticipate how our planet's climate might change in the future. This can help us understand potential risks and develop strategies to mitigate the impacts of climate change. Modeling is not perfect, and there are uncertainties, but these models are our best tool to forecast and prepare for the future. Through this modeling, we can anticipate and plan for climate-related challenges. At number 5, we have environmental systems modeling. This fascinating field uses mathematical models to capture the complex interactions within ecosystems, between different species, and the impact of human activities on these systems. Imagine the intricate web of life in a rainforest, or the delicate balance of a coral reef. Now, imagine trying to understand how changes in one part of that system might ripple through and affect the rest. That's where environmental systems modeling comes in. By developing mathematical models, we can simulate the effects of changes in natural resources, species populations, and human activities. For instance, what happens if a certain fish species is overfished? Or what if a new road cuts through a forest? These models help provide answers, and these aren't just theoretical exercises. The insights from these models are crucial for conservation efforts, guiding policies to protect biodiversity, and helping plan for a sustainable future. This modeling aids in conservation efforts and sustainable planning. Next up is traffic modeling. This fascinating field of study involves the development of mathematical models to predict and optimize traffic flow. Think about the intricate dance of cars, buses, and pedestrians that you see on the roads every day. Traffic modeling seeks to understand these patterns and make predictions about how they will change in different conditions. To do this, mathematicians use a variety of tools, such as differential equations and probabilistic models. These models can predict how traffic will react to various factors like a new traffic light, a road closure, or even the time of day. But it's not just about making predictions. Traffic modeling can also be used to optimize traffic flow. By tweaking different variables, such as the timing of traffic lights or the layout of roadways, we can create smoother, more efficient routes. And we all know that less time spent in traffic means more time for the things we love. Traffic modeling can greatly improve our commuting experiences. Our seventh topic is population dynamics modeling. Just as we can model human population growth, we can also apply mathematical modeling to the ebb and flow of species populations in an ecosystem. Think of a simple ecosystem where we have rabbits and foxes. Rabbits are the prey and foxes are the predators. The relationship between these two species can be described using what we call differential equations. In this scenario, the population of rabbits might increase without limit in the absence of foxes. However, the fox's population depends on the availability of rabbits for food. If the rabbit population decreases, the fox population will follow suit due to the lack of food. Conversely, if there are too many foxes, the rabbit population could decline due to overpredation. This dance between predator and prey, growth and decline, is what we capture with population dynamics modeling. It's a tool that helps us understand the delicate balance of nature. This model is vital in understanding ecological balances. At number 8, we have modeling physical phenomena. Physical phenomena are the observable occurrences in the world around us. They are the heartbeats of the universe, from the smallest particles to the vast expanses of the cosmos. And guess what? Mathematical equations can describe them. Yes, numbers and symbols breathing life into our understanding of the world. Take for instance the motion of particles. Newton's laws of motion, expressed as differential equations, can predict the trajectory of a thrown ball or the orbit of a planet. Or consider the propagation of waves. From the ripples in a pond to light waves traveling from distant stars, mathematical models capture their essence. Thermodynamics, too, isn't left out of the party. Equations describe how heat moves, how gases expand, and how energy transforms. So, whether it's the motion of atoms or the dance of galaxies, mathematical models are the lenses through which we view and comprehend these phenomena. This modeling forms the basis of our understanding of the physical world. Our ninth topic is social network modeling. Now, we're not talking about crafting the perfect Instagram profile. Social network modeling is a mathematical approach to understanding the complex connections within social networks, whether it's a group of friends, a professional network, or even the entire internet. At the heart of this is graph theory, a branch of mathematics that studies networks. Imagine each person in a network as a point or node, and the relationships between them as lines or edges. This forms a graph. By studying these graphs, we can begin to understand the structure and behavior of the network. Modeling allows us to analyze the diffusion of information and trends within these networks. Ever wonder how a meme spreads like wildfire, or how some posts go viral while others don't? Or how misinformation can propagate so quickly? Social network modeling can provide the answers by illustrating the pathways that information or trends can take. Social network modeling helps us understand the diffusion of information and trends. And finally, we have industrial process modeling. Now this is where mathematical models truly shine in the realm of industry. They are the unsung heroes behind the vast and complex operations that make our modern world tick. Industrial process modeling uses mathematical equations and simulations to optimize various industrial processes, from production lines to distribution networks and resource management. Think about it for a second. A factory churning out thousands of products every day, a logistics company coordinating deliveries across continents, or a power plant managing its resource consumption. These are all examples of industrial processes that are ripe for optimization. By applying mathematical models, companies can find the most efficient ways to operate, minimizing waste and maximizing output. They can predict outcomes, plan for contingencies, and make informed decisions based on hard data rather than guesswork. In the end, the goal is simple: to do more with less, to be more efficient, more productive, and more profitable. Industrial process modeling can significantly increase efficiency and productivity. So, as we've seen, mathematical modeling is a powerful tool. It's a bridge that connects abstract mathematical theory with tangible real-world data, allowing us to decipher intricate patterns and predict behaviors more accurately. From the population growth of species to the spread of infectious diseases, from economic trends to climate change impacts, mathematical modeling provides invaluable insights. It also aids us in understanding the complex dynamics of traffic flow, ecological interactions, physical phenomena, social networks, and industrial processes. Each of these fields is unique, yet they all share one common thread: the application of mathematical modeling to make sense of diverse and complex systems. This tool enables us to make more informed decisions, whether it's in public health, environmental conservation, economic planning, or industrial optimization. With mathematical modeling, we can better understand our world and make more informed decisions. Thank you for joining us on this mathematical journey.